kinds of lists. There's the empty list, which I'm going to write nil, and there's a non-empty list, which I'm going to write a cons. And an empty list, that's all there is to it. I just tell you it's the empty list, and then you know the list. A non-empty list, I'm going to tell you what the first element is, and that will be something of type A, and I'm going to tell you what the tail of the list is, and that will be something of type list of A. So, for example, a list of integers is going to be a list of integers. The list 1, 2, 3 is a list of integers. It's not the empty list, so it's not nil. So that tells you it has to be a cons. There are only two possibilities. It's not the first one, it has to be the second one. So it's going to be cons of something. It's going to be cons takes two arguments, so it has to be cons of two things. So it's the list 1, 2, 3. What's the head of the list? 1. Good. So that's the first thing. What's the tail of the list? So if the head of the list is, if you've got the list 1, 2, 3, and its head is 1, what's the rest of the list? Don't all shout at once. That was supposed to be good. Somebody shout at once. The range of the list, if you take the 1 off, is yes. So well, the remainder of the list is the list consisting of 2 and 3. So again, you write that. Is it empty? No, it's got 2 and 3 in it. So it's empty a cons. What's the head of the list consisting of 2 and 3? It's 2. What's the tail? Is the list consisting of just 3? Is the list consisting of just 3 empty? No, it's not. So there's the cons. My writing's getting smaller here. Space is getting smaller. What's the head of that list? It's 3. And what's the tail of that list? This time it is empty, right? So cons 1 and cons 2 and cons 3 nil is a list of integers. And then you can define functions over these lists. So here's the sum function. So given the list of integers, I can add them all together and make an integer. There are two kinds of lists, so I need to give two clauses to sum. There's a case for nil and a case for cons. In the nil case, that's all there is to it, because that's the whole of the list. In the cons case, I need to say it's cons of a list whose head is x and whose tail is x's. So what's sum of the empty list? 0. Good. What's sum of cons x x's? Plus x plus sum of x's. Right. So I have another list here, and I need to recursively sum that. Here's another one. Reverse is going to take not necessarily a list of integers. This will work for a list of characters, a list of booleans, and so on. A list of any type, and give me back another list. And there are two kinds of lists, nil and cons, so I need to give two definitions for reverse, two clauses. What's reverse of the empty list? Empty list. Now, a bit trickier. If I've got a list whose head is x and whose tail is x's, what's the reverse of that list? So I need to reverse x's, but then what do I do? So having reversed x's, I need to put the x on the end, not on the beginning. So it's something like reverse x's and then concatenate with the singleton list consisting of x. And the singleton list consisting of x is cons x nil. I say something like because I now need to define what concatenation of lists is on this on my new data type of list, not the built-in type of list. And there are lots of other things you could define on lists, and they many of them, not all of them, but many of them follow this form. There's two kinds of lists, so there's two clauses. There's one for the nil case, there's one for the cons case. In the nil case, you have some constant. Here it's 0, here it's the empty list. In the cons case, you do a recursive call on the tail of the list, and then you combine it somehow with the head of the list. So these two things have a lot in common. These two functions have a lot in common. So let's capture what they have in common. Look, I've got somebody else's stuff. So what do these two have in common? Well, that's it. There's two clauses. There's one for the empty list and one for the non-empty list. So let's write what they have in common. And the traditional name for this function is FLOLAC'. And I'll tell you why it's called FLOLAC' in a minute. This is supposed to be capturing the pattern. So there are two cases. One for the empty list and one for non-empty list. And so in the empty list case, what am I going to do? I have to produce some constant. It's a different constant in different cases, but for different functions. So I can't just plug in some arbitrary constant like 0 here because that wouldn't work for reverse. And I can't plug in nil here because that wouldn't work for sum. So I'm going to get back some constant. That's a varying part, so it better be given as a parameter to my function. And in the non-empty list case, I do a recursive call on the tail of the list. That's part of the pattern. You do a recursive call on the tail of the list, you do a recursive call on the tail of the list. That's the pattern I'm capturing. And you have the head of the list. And you do something with them. Here you add them. Here you plus them, put them together in the opposite order and do something to the x first. That's a varying part. What you do with those two is different for different functions. So we better assume that's a parameter as well. So let's call that f. And what you do is apply f to x and the result of the recursive call. So sum is an instance of this pattern, and for the empty list you produce 0, and the binary operator you use to combine the head with the result of the recursive call is addition. So in Haskell you can write the addition function by writing plus in parentheses like that. And reverse is an instance of this pattern. And in the empty list case, you get the empty list. And in the non-empty list case, well, you get this this funny binary operator here, let's call it f, where f takes the head of the list and the result of a recursive call, let's call it y's, and gives you y's plus plus singleton x. And that's what happens here. You take the result of the recursive call and you stick the singleton list x on the end. So the actual details of this don't matter. But what matters is that sum can be obtained by instantiating this pattern, and reverse can be obtained by instantiating this pattern. So this pattern generalizes those two functions there. And it's called fold right because if you apply fold right FE to a list, so a list with three things: cons x, cons y, cons z, and nil. That's a list of three elements. Then what I get is f of x and the result of doing a recursive call on the tail of the list, which is f of y and the result of doing the recursive call on the tail of the list, which is f of z and the result of doing the call on the tail of the list, which is e. So what this function does is it takes a list and collapses it down to a value, folds it up to a value, so that's why it's called folding, and the parentheses all collect at the right, which is why it's called fold R. There's another one called fold L that connects the parentheses at the left. But this is a common pattern where you take some algebraic data type and collapse it down to a value, and it's exactly the same thing we were doing with shallow embeddings. So these two functions have something in common and some differences. So what you do is you capture what they have in common by this pattern, and the difference here, plus and 0, or there, f and nil with this f, that's another algebra as it happens. And so folding and algebras and the shallow embeddings are all intimately connected. And even better, you can actually read this fold R function as a definition of the data type. That's called a Church encoding of the data type. I'm not going to say any more about that, but I will say this thing about deep embeddings, shallow embeddings, and the connection to folds. I think it's really interesting. It's not something I knew until, in fact, this time last July, I was giving lectures at a different summer school about embedded domain-specific languages and functional programming, and I was trying to work out what deep embeddings and what shallow embeddings mean. Lots of people have been using these terms. I didn't invent them, but I was trying to work out the essence of it, and I observed that the essence of it is about folds, and I think that's a new result. And I have evidence that other people think it's a new result because I wrote a paper about it, and it was accepted for ICFP, International Conference on Functional Programming, this year. So the paper's on my webpage. It's called Folding Domain-Specific Languages, and you're welcome to find. If you Google Jeremy Gibbons, you'll find me first. I'm the most famous Jeremy Gibbons in the world, and you'll find my webpage and you'll find that paper on it. I think that's what I was going to say. Yeah, there's another way of doing it, which I won't get into there. So I'm going to stop talking now. We'll take a short break, and then there are some exercises about a different language, so a slightly more interesting language than this one. And there are handouts somewhere. So if you want to get started straight away, it's the same URL, except it's called parser.pdf. P-A-R-S-E-R, parser. So you can download it from there, or Josh has got Stephanie to do some printing, so it's a 4-page thing that you can use PDF if you prefer. Any questions? No? Good? No? Thank you. Well, I should say, within the exercises, there's stuff for you to read and there's stuff for you to do. There's also stuff for me to tell you, because I ran out of time writing the exercises last night. So at some point, I'll stop you and fill in the gaps of what I didn't have time to type on last night.